So today I am going to cover new topics in some sense connected to what I said in the previous lectures, and they will involve basically linear algebra, but including the density matrix formalism to a certain extent. So the first topic, which is kind of straightforward to describe, is the uncertainty principle. And here I will be careful in separating two features. Okay. One part is something which is basically a mathematical property of non-commuting operators. And this is a very precise statement, and this is now understood or accepted as the correct formulation of the uncertainty principle. What is there, including in lots of textbooks, is a different statement of the nature that if you measure position of a particle, the momentum gets disturbed. That is not the uncertainty principle. Okay, there is a separate property which called measurement-disturbance relation, and by definition of measurement, it will involve projection of quantum states. This is also true, but it is analyzed in a very different framework, and that is to be separated from what I am calling the uncertainty principle. It's a different topic, and it will involve the projection. It has nothing to do with measuring what I call expectation values in a state where you don't have to refer to projection at all. So this formulation is expressed in the framework which was given by Robertson and Schrodinger. This principle is named after Heisenberg. Okay? And part of the problem is that Heisenberg confused these two statements. In his original works and whatever followed after, he sometimes meant this, he sometimes meant that, and that is the reason for many textbooks making statements which are not correct. Nowadays, these things are very cleanly separated, and this first statement, which is essentially a mathematical property following from linear algebra, is the one which is clearly described by the framework given by Robertson and Schrodinger. Okay. So, what does that formulation tells you? That it constrains expectation values of operators in some state. Okay. So now let me write a very simple identity and show how non-commuting nature gives you something else. So I start with two operators. They are quantum mechanical operators, so they are Hermitian by the axioms. And so there is a simple identity I can write is two times AB is equal to the commutator, and this is a notation for the anti-commutator, which means AB plus BA. This is AB minus BA. Now I can ask the nature of these two operators. So this is Hermitian and this is anti-Hermitian. So what happens when I take expectation values? Well, we saw that the expectation value of Hermitian operator is always real, and expectation value of a anti-Hermitian operator is just I times a Hermitian operator is purely imaginary. So then I can write the simple relation, Pythagoras relation or complex number of the expectation value of this particular object. Okay. So this is going to produce imaginary numbers. This is going to produce real numbers. So I write it in the squared version because I'm going to use a quadratic version to combine this real and imaginary part. So this is the expectation value of the left hand side square, which is equal to and put a modulo sign if you want, doesn't matter, there is an I, that is why I am putting the modulo sign. Nothing complicated in this. Absolute value square is imaginary part square plus the real part square. And it obeys a very trivial inequality that if I drop one of them, it is larger than the other one. Then I choose to drop the anti-commutator. So that's a very simple step, and I have not even used any particular property of linear algebra so far. So now I use a linear algebra relation which holds in any vector space, and that is called the Cauchy-Schwarz inequality. The standard form is that if I have inner product of two vectors, its magnitude is less than or equal to the product of individual magnitude. In the standard vector space, this will give A times B times cosine theta, and this just says that cosine square theta is less than 1. Okay. So what I have is an inner product here. Okay. So I can put a bound on it. And that is this object is now going to be compared to, well, depends on how you want to write it, but I will factorize it at one object is A acting on psi, which is a vector, the other acting B acting on psi, which is another vector. Okay, so A psi and B psi are vectors. And what is this? This is a inner product of the two, whole thing square. What will appear over here is a dot product or inner product of this with itself, which will means expectation value of A square, and this will become expectation value of B square. Okay. So you put everything inside it. This is greater than this, and then this is greater than that. So this stuff will be greater than this. Okay. So you get now a the expression for this. Modular signs are not necessary because these are all going to be real numbers, and they are squared, so they are all positive. This is greater than, I put an I, then even here the mod sign is not necessary, but let me keep it. This. So daughter. Huh? Okay, thanks. Okay, and this is essentially the uncertainty principle. What is done commonly is write this as a not the square of the operator value, but express what is known as a variance. Okay. So that is a kind of a straightforward how to get the variance. So replace the operator by subtracting of its mean and do the same for the other operator, and the consequences for this thing is commutator of this is the same as commutator of that, because we are just subtracting number, it will just cancel out. And so now I have the common form of the uncertainty principle in this framework, which is so this is a general form. The common illustration of this is made using the properties of position and momentum. Okay, that is the most commonly used structure. So there is a notation for all those things. So, example. So this is a fundamental relations between position and momentum, and the commutator has the Planck's constant sitting inside it. Here in all these things I have not bothered to put any units, so the Planck constant is actually not there, or rather it's not needed here in this derivation at all.
In the brackets, d minus
there is probably a 4 lost somewhere. That's yeah, there is a 4. Let me see, how does it go? This is this, it is greater than this, so this stuff is there, so there is a 104.
Square is for d minus. Square is for d minus.
I'm making mistakes. Fine. So what this is the variation from the variable from its mean, and it is squared, so it gives this variance, and then you have the other notation, writing the variance is given by this symbol delta x square, and then there is a delta p square, and it's greater than or equal to h cross square by 4. So this is a formula you will find in lots of textbooks, probably even in high school books these days. But that is a consequence of this much more general formula. And you can try it. It involves these operators. The operators need not be just a number like this, where this will just come out as a constant on the other side. But you can try operators where there is something non-trivial left over here. And something which you already know in quantum mechanics, where there is a non-trivial version which you can express for angular momentum. Where for the particular case where the angular momentum is half, these things are just polymatrices, and we know what the anti-commutator will give. It will give, and because it's twice, it is actually 2. So this relation can be used to also constrain the expectation values of angular momentum components. The simplest thing is just j equal to half case, which is qubit. That is what we will deal with most of the time. Put sigma 1, sigma 2, and sigma 3 and see that they are all not arbitrary, they are related. You can take some simple states like eigenstates of say sigma 3, then the right hand side will be very simple. Eigenstates are only plus or minus half, and because of the square, whether it is plus or minus half doesn't matter, and things actually simplify a little bit. It will tell you what happens to the other components of the angular momentum. But this is a generic situation and it works. I mean, there is nothing complicated inside here. All kind of things which are generally written for this relations, that there is a Fourier transform involved and the conjugate variables are there. None of that is necessary. All you have are non-commuting operators. Okay, there is no reference to Fourier transform in the general phase. Now, this appears only for conjugate observables which are like this. The position and moment are conjugate variables, and then it will obey this relation, which is something which will follow from Fourier transform as well. But here, if you look at in this notation, there is no Fourier transform reference at all. The identity is still valid. So this is something which is very straightforward and very simple, and you can remove all kind of unnecessary statements which are reference in saying the uncertainty of variables is this way, that way, etc. And there are counter examples one can construct that will kind of give a contradiction, because many times the expectation values don't have to be measured. They can be inferred. Okay. For example, I look at position and momentum. I measure the position at some stage, it is here. Another stage, it is here. The two positions I can measure independently. They are commuting operators, no problem. And then by just subtracting the two coordinates, I can estimate what was the momentum. I don't have to measure the momentum to figure out what happened in between, and that is completely legitimate. You move from here to here, you know that time, and you calculate the expectation value of the momentum, nothing wrong with it. And that is where the trouble arises in this interpretation, that you measured the position, the momentum became uncertain, but you don't have to measure the momentum at all, you can just infer it. And that is a caveat which you should watch out for. And I tried to give this derivation in detail to illustrate what is necessary and what is not necessary.
If you can infer the momentum by calculating the position also, then what is the significance of measurement? If you can,
it will give you the expectation values if you calculate in that particular state. But the point is that if you do an inference, the uncertainty goes to zero. You are not measuring the expectation value in the same sense. The expectation value will involve figuring out what the state is and then calculating the answer. Here you are not bothering to find out what the state is. You are just looking at the results of the measurement, which are fully classical. Okay, because position, you can measure just one variable to as much accuracy as you want. There is no restriction coming from quantum mechanics. And measured value is a classical value, some number. And that you can use to infer whatever happened in between. You are not doing a calculation of a quantum expectation value at all. And that is fully legitimate. There is nothing wrong with it. This says if you want to measure the expectation value in the particular state, you will obey this kind of relations. Okay. Now, let me see. Yeah. One more thing I need to connect various things I have said. It was done partially earlier, but these are all definitions which I need to clarify. That multi-particle, or rather I should write multi-component. These are described in in the tensor product notation as I said earlier, and you can use the tensor product definition both as a vector in the Hilbert space part, or you can also use it for a density matrix if you want. That doesn't cause any problem, but a very simple structure arises, and that is what I call entangled states. They arise when the components cannot be factored in any basis. Generically, you will have situations where factorization will work in one basis and it will not work in the other basis. There are all kind of situations like this, but this can be just written as psi is not equal to product of two factors. If this doesn't happen, we'll call the state entangled. And it's very common because there will be a basis for the tensor product for psi 1, another basis for psi 2, and no matter what I try to do in taking a product of these two, I can have situations where there are multiple components which mixed up. I cannot just factor them. If that happens, the states are entangled, and otherwise the states are called separable. And one thing I can mention here that once you go to a density matrix and mixed states, you can construct statistical mixtures, and statistical mixture of separable state is still considered separable. The individual objects, they completely factorize, and that is good enough. This is a matter of definition because, well, these words appear, entangled states, separable states, in describing a lot of phenomena. From the point of view of mathematics, these labels are not needed because if you work out the algebra, everything is just a combination of multiple components, some linear algebra, superposition, everything which is there. If you want to give it an extra name, fine, go ahead and give it. If you don't give it an extra name, doesn't matter, the mathematical expression remains the same. But these labels are there all over in the literature. Yeah, so I can now describe an example which is very commonly used, is to create a what you call superposition of a large number of states. Okay, so this is typically the starting point of most quantum algorithms. If you don't use superposition, you are not going to get anything additional to whatever already exists in the classical system. So you start with a 0 and multiple components, all factored in this tensor product notation. A register with n qubits. Now what you can easily do is rotate each qubits into a new basis. It's a two-dimensional space of 0 and 1, and you can rotate it. So I choose to rotate it by 45 degrees. Okay, in the 0 to 1 notation, and I can reach there. It's just a redefinition of the basis for each qubit, which is done very often in lots of algorithms. And what this requires is n single qubit rotations. It's a redefinition of basis, but we'll say that basis is fixed and we rotated the state. It's a subjective statement, but you can always do that. And now you try to write it down by brute force. What this product contains. Okay, and then you will discover that there is a normalization, which I just put outside. And what is 0 plus 1 to the power n? To take a product, and I will write it in a explicit form. That each or let me write the tensor product more explicitly. Each one had two terms, which is I1 is 0 or 1, I2 is 0, 1, whatever it is. And these are the individual factors. And this now can be run in a more compact notation. There, these n components are just labels for n bits. And what we have is here all possible values of I with equal weight. It's called a uniform superposition. How many components are there inside here? 2 raised to n. So it's a large superposition. But on the other hand, it is entangled. The answer is no. It's completely factorized. All this side is just this. This is not untangled, and is produced with AND operations. So this is where you see the power of superposition combined with this tensor product notation. That with an operation you can superpose 2 to the power n components. It's linear, that is exponential. And this is most of the time the first step in any quantum algorithm. And after doing this, you can apply a unitary operator. It will transform all the 2 raised to n components in one shot. This is a version of parallel computing. Yeah. Yeah. This. So what do we have here? You have 2 raised to n components evolving in parallel. But what is the hardware? Hardware is only n qubits. If you wanted to do this in a classical component language, 2 raised to n components, you will need 2 raised to n parallel boxes. While you are doing this with much smaller number of hardware boxes. And that is a power. It's a exponential in this very simple situation that you can do large amount of parallel processing with limited hardware. Of course, this is not the end of the story. At the end, you'll have to do some extraction of the result out of this 2 raised to n components, and that is actually the crucial part. But the first step is essentially do a large amount of parallel computing, and that can be done with a exponentially advantageous situation as far as the hardware is concerned. So and then suppose you did this large parallel computing and you got some complicated states, okay, 2 raised to n components. Now you want to measure the output. What is allowed? You have only n qubits available. And so you can measure only n values, 0 or 1, nothing more. Because even though there are large number of components, they are not separate things in the hardware. So only n because that was the hardware, you can't do anything more. And so what happened to all the 2 raised to n? Projection. It is lost and lost forever. So other and this decides whether your computer is useful or not. Somehow the problem is such that, and the algorithm is such that when you do this projection, the result is nicely in these n bits. Then it is great. But the problem is too complicated result, you cannot put it in n bits, then all the stuff is lost and your efficiency or advantage, whatever you want to call it, is not there. Okay. So the overall advantage is problem dependent, and there is a mathematical description about when can this projection be good. Okay. You had 2 raised to n components and you want your answer to come only in these n bits. So it is a large space, but only a small space you want the answer to come there. And the mathematical label for this, if you encountered before, it's called a delta function. Delta function brings the whole distribution in a narrow region. If you can do it, well, you have a great algorithm. If you can't get a delta function, it is spread all over, you measure it, it is all getting lost. So the delta function will have descriptions of many different types. So good algorithms have results as and all the game is in this particular step. Can you construct an algorithm which will narrow down this distribution? You have to know the details of the problem, you have to know all mathematical tricks which can be used to manipulate the distributions, whatever it is. And there is no, what you call, recipe for this. It's all done by trial and error. So people try out various problems. If they succeed in doing that, okay, you have a great algorithm. If you don't succeed, well, try something else. And that has been the case now, whatever, 30 years. Nobody has found any better way of understanding this, and it remains a what call challenge. Can you do this? For developing a good quantum computer with whatever efficiency, which will be very different than the classical version where you say that I have an advantage. It's a open problem except for some selected situations that yes, you can do this. Of course, there are counter example also which are against special situations where you can't do anything, in the sense that there is no way to compress the answer to the delta function. And then you can say that for this problem, the quantum computer is not going to give you any advantage. But those are all selected problems depending on what you can do with these distributions over a large number of possibilities. Okay. So these are some general comments, but it are important to understand what we try to do. When you say I want to do quantum computation and make something solved very fast or very efficiently, etc., there is no hard and fast rule about how that can be done. But this is buried inside every analysis of every algorithm in some sense or the other.
One question. So, using delta function, can we express 2 to the power n components into as n components only?
Yeah, that is the job of the delta function. Can you compress it? If you can't compress it, well, it's fine. Nothing you can achieve.
So the typical delta function compresses to a single value. How can we say
It's a little bit of an extension. It doesn't have to be one value. It can be n values inside here. But n is still far too small compared to 2 raised to n.
So does that mean these I1, I2, I3s, suppose I1, I2, I3s got one common value?
Yeah. You have to find, as I said, this is going to be a problem-dependent situation. In some cases, it will work, and we'll go through the algorithms later in the course, and I will point out how this so-called delta function appears. Well, one answer I can give right now, because I earlier mentioned Fourier transforms. Okay. So, delta function arises very easily when flowing with Fourier transformation. If you have a periodic function, you Fourier transform it, it gives a set of delta functions. But a delta function is basically the periodicity. And that is a important algorithm in this particular context. If whatever manipulations I did with the processing in the evolution, suppose the answer is periodic. Initially it was all a constant, but after some manipulation, these various states came, but whatever the coefficients are in periodic in some sense. If that happens, then I will do a Fourier transform. The periodic function will now become a delta function, and then I will do the measurement. And what I will get out of it is the information about the periodicity of the function, nothing more. I will not get the distribution, I will only know that the function is periodic. If knowing the value of the period helps me in solving any problem, then it is good. If it doesn't help, then this strategy will not solve the particular problem. So this is one possibility, but you have to now ask under what situations this function, which is distributed all over the place, can be made to get compressed into a small number of components. For periodic function, Fourier transform does the job. Nobody knows the general answer. Some other distribution is there, not necessarily a periodic function. What can I do? Well, work through various possibilities in algebra and see anything comes out. So next I want to specialize not in this multi-component system, but a system which has only two parts. Each of the part can have many components, that is fine, but I'm not going to divide it into many parts. I'm just going to take the whole thing and insert one partition somewhere in the middle and ask what are the things that I can learn from this bipartite situation. And this turns out to be a very general description for many physical phenomena. What are the two parts? And I can write down several specific examples which will come. So this can be it can be, say, simplest thing is to just have two qubits. I can have two registers, each will have some number of qubits. But much more interesting situations arise well, I divide the whole description into this is the system and that is the measurement apparatus. Both are behaving quantum mechanically, that is fine. What are the things that will happen? And this turns out to be a important setting to understand what happens when you try to measure a quantum system. And even though we don't have a full understanding, what is appearing all over the place, like projection of the state. Some eigenstate appears, everything else gets lost. You want to understand the dynamics of that. And projection is just an instantaneous label, sometimes called a collapse of the state. If you want to understand the dynamics, you have to go into this description where you take the system, you take the apparatus, you define the interaction between them, and which will produce some evolution of quantum state, and ask what happens between the system and the apparatus. And much more widespread situation is the system and its environment. We don't know anything about the environment at all because we basically throw out. Your system, it's interacting with the environment, I can't avoid it, but something happens and I have no control over the state of the environment in the sense that I cannot measure it. I can measure anything I feel like on the system, but the environment is unobserved and the environment can be as large as the rest of the universe. Whatever it is. Our quantum system is just here, everything else which is outside is the environment. What happens in that particular scenario? In every physical system you have to ask that particular question, and there is a label which is often used, that these things are called open quantum systems. Part of it is under your control, the other stuff is not under your control. So all these problems can be handled if you develop a mathematical framework for describing bipartite quantum systems. We have all the axioms and we are just going to do it step by step. And the first concept which appears in this language is called reduced density matrix. In some sense, you have to go to the language of density matrix, because what happens many times in this bipartite system, you end up with mixed states. And there is no way to describe the mixed states using the vector in Hilbert space language. You have to go to the description of a density matrix structure and introduce this particular concept. Many times there are many other names which also refer to partial trees. What is the definition? That if I have, so this is, let me put it, the density matrix in some space, this bipartite system, I'm just going to label with some index A and some index B. And so this rho is a big matrix with lots of indices corresponding to A and B. The reduced density matrix removes some of these particular indices by taking a trace over all the indices corresponding to one of the parts. Okay, it's a matrix and I can sum over some subset of the indices, and the trace means that the summed over components are all diagonal, whatever it is. The off diagonal part disappears when you do this. So this is generically mixed state, and the reason for this is the off diagonal parts coming from B are lost. They are there in this full description, but when I took a trace, that stuff is gone. So this is a definition. Why it is useful? Well, for the very simple reason that we have defined the expectation values in the density matrix language. So look at expectation value of an operator which is defined on one part and nothing on the other part. That means identity matrix. It's typically the situation in this framework where you have an operator on the system which you want to measure, and the environment you don't have any control, you are not doing anything. Now what will the expectation value of this thing look like? So we have this definition, O is equal to trace rho AB times so this is a tensor product, something on A, nothing on B, and this is a object with both indices A and B, and this now everything has to be summed over to obtain the expectation value, which is a number, which is a trace of all the components. And now I can see that I can separate the trace over the part B rather trivially, because this stuff is identity. So if I perform a trace over B, I will only have trace acting on this first part, nothing on the second part. And that exactly gives this structure, that this is equal to trace over A rho A reduce times by definition. And that tells me that I can still calculate the expectation value by looking at only one part, which is A. Because this definition is identical to this, except for the indices, provided I know what is the reduced density matrix. By the same structure, that there was a formula, here I am just using the same formula on a subset of variables, but I have replaced this original density matrix this by the reduced version. And that is perfect, because all I am doing is looking at that subset, and I wanted expectation value and I can get it out. So rho A reduced has all the information to obtain expectation value of all operators, and so O is this. If you want to calculate this, all I need to do is find out this reduced density matrix and then just apply the usual rules of calculating all observables, and that will give me everything I want to know about the system. So system had some number of operators which I want to measure. I can get those things out provided I have a reduced density matrix. The caveat is that this reduced density matrix will be generically a mixed state. It will not be a pure state when this open quantum system environment is present. So this is a concept, as I said, the definition is just this. Because it's a trace on one component, it is also called a partial trace, etc. But this kind of generalization of the classical probability theory. Suppose there is some distribution, many variables are involved, and I can say that the distribution depends on some x1, x2, x3 up to xn. And then what is the probability of x1 having some value? It is just take the whole distribution and sum over all the possibilities of x2, xn, etc., because they are not going to change the value of x1. All the values of various other components, you just do what is equivalent to a partial trace, which is called partial sum. So if I have p of x1, then it's essentially equal to x1 is a standard rule in statistics. You have a multivariable distribution. If you want to find out a distribution corresponding to only one component, sum over all the other possibilities. And this is a generalization. In the quantum language, what does the sum over everything else which you have not observed? Well, it is equivalent to performing a trace, partial trace. You don't have probability distribution, you have density matrices, but as I have mentioned before, density matrix is just a logical generalization of what to do with probability distribution. And well, this mathematical formula are kind of complicated expressions and you have to understand the meaning. So let me take some just 2-qubit states just to illustrate how this works. And I will write it in some combination which I have used here. So state is 0, 0 and 1, 1 with some coefficient a and b. What will happen when I do this partial sum over one of the variables? Okay. Well, first I have to construct the density matrix of this particular state, and well, I will write it down. This is a pure state. So the density matrix is just going to be this multiplied by its adjoint in a order, and all the components which are there will appear somewhere. There will be 4 by 4 matrices because each one has 2 components, so you will have 4 terms, and write it in some language. Okay. The 16 numbers which appear in some thing, there are only 4 ones which are non-zero, which are all products of this. This is diagonal 1, 0, 0. There's a off diagonal one, which is this multiplied by that, etc. Now what happens from this if I perform a partial trace? So now you have to ask, well, partial trace means I will take this matrix, it has all the indices, and sum over the possibilities where the component of B is diagonal. And well, you have to count whatever you have to give some label 0, 0, 0, 1, 1, 0, 1, 1, etc. for all the indices, and then find whatever it is, the off diagonal terms where these components of B are not the same, will kind of disappears, and that will be the term like when are the components of B are not same, that one side is 0, the other side is 1. I'm just multiplying the two things together. So this you multiply by itself, you will get 4 terms. 2 of them will have the component 0 same, which is 0, 0 and 1, 1. And 2 of them will have different, which is 0, 1 and 1, 0. So the 0 and 1, 0 I have to throw out. The other one will remain. And so if you calculate what is row A, which is a reduced, it will be now a 2 by 2 matrix, and its values will be only the diagonal parts. And that's what remains. The diagonal parts is this multiplied by itself and that multiplied by itself. So a projection has occurred. Okay. And this is actually a description of measurement of a single qubit. You got a probability distribution directly out of it. You will get 0 with probability A square and 1 with probability B square. And this density matrix is a mixed state. There are no off-diagonal terms. If you calculate rho square equal to rho, that will not work because this is not a projection operator. So all these kind of manipulations, they are important in understanding many of the problems which I have mentioned, how you deal with projections, how you deal with environment, and everything is based on this concept of this reduced density matrix, which is basically saying what happens to a system when you do not control part of the variables and you only look at other part and what is the information available there. And there are lots of powerful properties which can be now built on this definition. And that I will do next time. But this is a very important concept, and it gives a lot of relevant ideas about what to expect in dealing with quantum systems in its kind of full generality.